We'll start focusing our attention now on the idea of vector fields. Now, why would we be interested in vector fields to begin with? First of all, they're really nice for modeling physical phenomenon, such as studies of fluid dynamics, looking at ocean currents, wind, um, fluid through a pipe, that sort of a thing. Also, very commonly used to calculate the amount of work done by a force field. Now, a force field, it's not like Star Trek. We're talking about the forces that move an object. We're not talking about your sci-fi force field stuff here. And also, real valued functions, when we think about it, really only move in two directions, either the increase or the decrease. And on the other hand, vector valued functions can change in terms of magnitude and direction. So unlike real valued functions, which have single values representing the rates of change, vector valued functions have rates of change that are actually vectors. Now, these properties make vector valued functions really ideal for modeling physical phenomena in 3-space. And that's what we're really talking about here. We're talking about these vector fields are vector valued functions. So let's go ahead and take a look at a definition for what a vector field actually is. We take a look at both 2-space and in 3-space. Now, a vector field in 2-space is a function, f of xy, whose value at a point xy is a two-dimensional vector. Now notice this function f is in fact a vector. Now, likewise, in 3-space, this function gives me a three-dimensional vector at this point x, y, and z. Now, take a look at this. This may be a little bit hard to see on the video, but this is a vector field, and each of these little marks here are actually lines. They're vectors. And what these vectors are showing is velocity of currents in the Gulf Stream. So all these little vectors are actually showing direction of current and the velocity. That's what all these little lines actually are here. Now think about this in terms of like fluid through a pipe. So let's see, let me draw a pipe here. And I'm going to make it narrow on this end. And then let's make this pipe something that kind of gets bigger. And I have fluid coming into this pipe. Now, if these vectors represent the velocity of the fluid coming into the pipe, then what we expect to see is as it gets further and further into the pipe, the velocity is going to decrease because it's bigger here. And ultimately, we're going to have really small vectors. So this would be a vector field that would represent fluid dynamics, showing the flow of a fluid through a pipe. Now, each one of these vectors is attached to coordinates. If this is in 3-space, these coordinates are going to be coordinates x, y, and z. And then this vector is going to be based on the vector function. Now, very commonly, it's very useful to write vectors in component forms, or the vector functions in component forms. Since the vector function f of xy is a two-dimensional vector, we can write it in terms of the component functions p and q, and likewise for f of x, y, z. So for this vector function f of xy, I can think of this as p of xy I plus q of xy j. And likewise, if I'm in 3-space, function of x, y, and z, I'm going to think of this as p of x, y, zi plus q of x, y, z, j plus r of x, y, z, k. Now this is a very convenient form to write this in terms of trying to visualize and figure out exactly what's happening to this vector function or what the vector field is going to actually look like. Now just as we did with vector functions, we can define continuity of vector fields and show that f is continuous if and only and if the component functions p, q, and r are continuous. So if we have continuity into the component functions, then the vector function is also going to be continuous. Now, commonly we identify the point xy in 2 space and xyz in 3 space by its position vector. R, the vector r, equals xy, or xyz if we're in 3 space. Then it's very useful to think in terms of vector function becoming a function of a vector. So f becomes a function that assigns a vector to a vector. So think about this for a moment. Let's just draw in 2 space xy axes. Now the idea behind this vector function f of xy is I have coordinates out here somewhere xy, and this is going to be the tail end of my vector. So starting at this point, this function will tell me where my vector is going. Perhaps it looks like this. So this is the vector function f. But if I think of xy as the position function or a position vector r, now I can think of f of this position vector r. Hence the idea that we're taking a vector r and assigning to it a vector. Now, likewise in 3 space, it's a little bit more difficult to draw. If I have a point in 3 space, say right here, that has x, y, z coordinates, and then my vector function f of x, y, z may be like that. But once again, if I think of this point x, y, z as a position vector r, then I can think of this as simply being f of r. So that's the basic idea of what a vector field is. Now in reality, we can't draw a vector field. We can't produce a real vector field on a computer because it assigns, if you go back to the definition, it assigns this vector to every point in 2 space or every point in 3 space, which means there's an infinite number of vectors. Rather, what we do is we either draw by hand or use a computer to aid us to complete a diagram that's a representative of what the vector field looks like.